Good morning, aspirant. Hope you all are doing well, your days are going productive, and you are doing excellent in your studies. So, in the last class, we have completed our discussion on commutator. Basically, commutator was a property of operator. We started our lectures on operator and different properties of operator, right? One property we have seen that different variables or observables, better to say, observables. Then we have seen the commutator and their properties of commutator. Then few numerical problems. Then we have seen the with these numerical problems we have seen few formulas. Okay. Then the next property. Next property says operators in quantum mechanics must be linear. Just write with me in this class. I will provide you a few notes in this format, in written format. I will write with you and you have to note down with me. Operators in quantum mechanics must be linear. This is the sixth property. Now, operator is basically a mathematical tool. When we started operator with this definition, I have told you that it's a mathematical concept. It's a mathematical tool. When we are going to use this mathematical tool in quantum mechanics, we have to mold our operator in that way that we can apply it in quantum mechanics. For that application, for example, I have one pen. Okay, suppose I am going to use it in some way. For example, I have this pen in my pocket and I am going alone in a road, and some criminals approached me to snatch my phones and something. So this pen will save me. It is a life-saving object for me for that time. Life-saving object for self-defense. So I am molding this pen. I am molding the use of this pen according to my convenience. Okay, but the pen was not made for that. Similarly, operator concept was a purely mathematical concept, but we are borrowing from mathematics to use it in quantum mechanics. For that, we have to change the operator. We have to not change, basically, we have to impose some conditions on operator. For example, if I use this as self-defense, the sharper the tip will be, that will be more beneficial. Similarly, every operator cannot be used in quantum mechanics. Okay, so the operator must be linear. We will be understanding what do you mean by linear operator. So my operator should be linear to be applicable in quantum mechanics. So operator, basically we must have a linear operator. We must have a linear operator to be used in quantum mechanics, right? So only operator is not enough. We must have a linear operator. When we will call an operator a linear operator? Suppose I have one constant c into f of x, a function, plus d constant is a constant. Then there is another function f dash x. So total it is a function, overall it is a function. Okay, summation of two function is also a function. Suppose my operator is a. If the result is c a f of x plus d a f dash x, that means operator must not function on constant entity. That's why constant is outside. Okay, so operator will not operate on constant, and operator will operate on functions additively. Okay, so separately a can operate on both fx and f dash x. F dash is not ddx of x. Okay, f dash means a different function of x. Okay, we can write it gx also. Okay, so this is the criteria. If my operator fulfills, then I will call it a linear operator. That means if we write it like two conditions, that is, linear operator do not operate on linear operator do not operate on constant. Linear operator do not operate on constant. Linear operator operate additively on two functions that are linear. Two functions that are linear. Linear function means you have just written like something plus something. Two functions are linearly joined. We know linear combination, isn't it? In atomic orbital theory, there is a concept of LCAO, linear combination of atomic orbital. So linear combination means if g of x plus f of x, two functions, two, three more functions are joined together. Okay. So if there is a function, my operator should operate separately on two function, and it should not operate on constant entity. So constant entity will be written outside. That's a simple thing. Okay. For example, let's check. Let's check whether my DDX operator. Question is, DDX operator linear or not? Linear or not? Let's check. Let's take this type of function, a random this type of function. Suppose a constant, let's say 3. F of x means मान लो what is this is x square plus 5 f dash x, it is just assume it x cube. So let's operate ddx on 3x square plus 5x cube. Just to check, to first check it is a linear operator or not, you can just, there are two property. One is additive and one is multiplicative. So any one property you can check. So can we write it like this? Just equal to, if this is true on and a is ddx, will it be true? C means 3 ddx of x plus d means 5 ddx of f dash x means x cube. For ddx operator, is this true? Yes, we know this is true. We know this is true, right? In normal differentiation, we also write it like this: 3 into ddx of x square plus 5 into ddx of x cube. We in normal differentiation, you will write like this. This is obviously a linear operator. So our answer is yes, ddx is a linear operator. Now, next question. Next question is identify the following operators are linear or not. You have to just identify the following operators are linear or not. I will be giving you 4 options. A, integration. B, square root. C, SQR means square. SQRT means square root. D means log. These are 4 operators. Are they linear operator or not? You have to just check. This is the first question. Just take You can take a random function for that. For example, 5x square. Okay, this additive something you should you can ignore it. Okay, no problem. Okay, let's take 5x square is a function. Okay, but if we can write it like this, you will be obviously can write it like this. Integration, let's check. Integration of f of x 5x square, if we can write it like 5 integration of x square, it is linear. Square, if 5x square, we can write it like uh, yes, 5x square, we have to operate a square on it. If we square it, is it the same thing like it will not operate on 5? It will operate on square only. This square is this not this 2 is basically the function. Okay, square root 5x square root, is it the same meaning that 5 will root will not operate on 5, will operate on this only? Log of x square, sorry, log of 5x square, does it mean 5 log x square? This is true, this is not true, this is not true, this is not true. So this is linear operator, this is not linear operator. Clear how we will identify one operator as linear or not? Okay, if this does not satisfy, then obviously if we take plus 3y plus 3x cube, yeah, something like that, then obviously you will get the same result. Okay, so my integration is a linear operator. Similarly, differentiation is also linear operator, but the square root, log, these are not linear operators. Okay, now next, few points on linear operator. Okay, just few properties you can say, or few points on linear operator. Linear operator always commutes with constant entity. Constant entity, linear operator always commute with constant entity. What does that mean? Linear operator always commute with constant entity. Suppose A is our linear operator, small a is constant, psi is a function, psi is a function. Now linear operator, I am saying linear operator is always commute with an constant entity. So to check whether linear operator commute with constant or not, we have to write the commutator of with a constant. If it is 0, then you will see commute. If it is not 0, we will say it is not commute. Let's check. Any function, if it's a any function, any operator a and constant entity, if my arbitrary function is psi, then a minus a psi. Now a is a operator, linear operator. That means the constant will go this side. So small a minus a small a. This property is due to that from the definition of linear operator, psi. That is basically a psi minus a psi. That is basically 0. That means always a linear operator will commute with a constant. Second property or second note. A linear operator, sorry, it is not a property of a linear operator. I just write it like this. I'm not getting eraser option. Okay, say any operator commutes, any operator commutes with itself and its power. If there is any operator that always commute with itself and its power, that means any operator, suppose my operator is this, my operator is this, itself means this and its power means this. So these two always commute. My statement saying this will always commute. So a comma a to the power n will always commute. That means a to the power n psi minus a to the power n a psi equal to 0. Commute means this. That means a to the power n minus a to the power n a equal to 0. Or first you operate a on psi, then a to the power n on psi, it will be same as first you operate a to the power n on psi, then operate a on psi. That is basically the same thing. Okay, so any operator commutes with itself and its power practically means a comma a will commute, a to the power n comma a will also commute, and a comma a to the power n, a and a to the power n, this will also commute. This is our second property. It is applicable for any operator. So if any multiple choice question comes that only linear operator commute with itself and its power, then no, any operator. Okay, now we have not finished this this case. What is the implication of this statement? Suppose my two operator is tx means kinetic energy, and px, that is momentum, kinetic energy along x direction, and linear momentum along x direction. Its corresponding operator is this. Will they commute with each other? Let's check. Tx means px square upon 2m. We know, we have already seen this. Tx means this, comma px, right? Now we can take common this 1 by 2m outside, 1 by 2m. If you want to check again, you can just split it, this into this minus this into this, then you will obviously get common of 1 by 2m. That means AB minus BA, if we break the commutator like this, then you will, in both cases you will be getting 1 by 2m, then you will take common of this. Px square comma px. Fine, no problem. This is basically 1 by 2m, and we know that any operator and its function and its power 1 and its power 2, they commute with each other. That means this commutator basically value is 0. That means 0. That means kinetic energy operator and linear momentum operator commute with each other. So just write the statement: kinetic energy operator and linear momentum operator commute with each other. Okay, got it? Next property or next point. Two operators with multiplication as operation always commute. Two operator with multiplication as operation commute. What operators we have seen? 4 5 operators like position, momentum, kinetic energy, potential energy, angular momentum, and these operators we have seen. Among these, which operators are multiplicative in nature? If you have revised well, you can tell me that only position and potential energy operator are multiplicative in nature. So these are multiplicative in nature, potential energy. Position, how we denote position? X or Y or Z. How we denote potential energy operator? Vx, Vy, Vz, right? So these are potential energy operator or kinetic position operator. These always commute. What does that mean? These always commute means if we put x comma y as a commutator, it will be 0. X z will be 0. X y will be 0. Yx will be 0. Zx will be 0. Yz will be 0 for every combination. X operator, Y operator, Z operator, position operator, Vx operator, Vy operator, Vz operator. This will commute, 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 this will commute. Let's do it again. It's funny. So X operator, yeah, Y operator or Z operator or Vx operator or Vy operator or Vz operator. That means position along x direction. What is the practical name of this operator? Position along x direction. Position with respect to or along y direction. Position along z direction. And this. This will operate and this will commute with this. That means x cap comma y cap third bracket will be 0. This will commute. 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 This will commute in both the direction. Obviously, each and everything in both the direction. Next, x vy will commute. Vxy will be commute. Yvz will be commute. Vyz will be commute. X Vz will be commute. Z Vx will be commute. Each and every possible combination, they will commute. Okay, they will commute. So this is the practical implication. Okay, so two operators with multiplication as an operation always commute with each other. Okay, then next one or two properties left, we will do it in the next class. Thank you.